Good afternoon, guys. This is Professor David J. De Los Reyes, an electrical engineer by profession. I know something on electronics because I have trained on the hands-on troubleshooting here in the USA. So I got also an experience on hands-on troubleshooting of electronics. Okay, let's proceed, guys. My topic this afternoon will be a new topic. The topic is still a variable separable differential equations. So under my channel, under the lesson DE05, differential equation number 5, on my channel, on the new subject matter differential equation, subtopic first order. Okay, and the main topic is variable separable. The kind of differential equation is actually variable separable. This is with number 3. Number 3 meaning this will now be my third example on the so-called variable separable differential equation. It's a different variation of problem. Okay, I will try to read the problem. We are given dy over y equal to dx. The initial condition is x equal to 0 when y is equal to 2. The given differential equation is dy over y equal to dx. This is a differential equation. It contains derivative, right? It contains derivative. Or differential. This is just y. Without the y at the bottom, this is dy and dx. So if an equation contains differential, it is supposed to be a differential equation, okay? Okay, let's try to bring out the solution. We will write the given original equation, dy over y equal to dx. Okay? We do not have to do something. The variables are actually separated. It's separated already. Because on the left hand side, this is dy and y. Right hand side is just pure x. Okay? So wherever the location of x, it's just simply x. And for the location of y, it was just simply y. So actually, we have separated already the variables. Taking the integral of both sides. The integral of dy over y equal to the integral of dx. What you will do on the left, do it on the right. Okay? After placing the integral sign, integrate. So we pass by integral calculus. So whatever kind of integration that we will be encountering, just apply it. Okay? That is from the simplest integration to the most complicated integration. Okay? Just pray that the integration will be easy. Okay? So it's just like on the board exam. If they give you an integration problem, you don't know what kind of problem the examiner will be giving you. So it's a must that you know the integration from the simplest to the most complicated one. Okay, let's try to integrate. The integral of dy over y, it is under the form the integral of du over u. And the integral should be the natural logarithm of u. Right? For the left hand side. For the right hand side, no problem. The integral of the differential of any variable is just the given variable. So the left hand side will be natural logarithm of y, we are following this, equal to the integral of dx is just simply x plus a constant k. Okay? Taking the antilog of both sides. For natural logarithm, the base is actually equal to e. So if we raise both sides of the equation by e to the natural logarithm of y is equal to e raised to the quantity x plus k. What you will do on the left, do it on the right. The antilog of the left-hand side should be the antilog of the right-hand side. And e to the natural logarithm of y is just y. That is laws of logarithms. Okay. E to the natural logarithm of u as a rule is actually u. Okay? So the left hand side will be equal to y. The right hand side, it will be e to the x. The exponent of e on the right hand side is actually a sum. And we could rewrite this one as simply e to the x times e to the k. Because if we try to multiply this one, the compressed equivalent is actually e raised to x plus k. So actually we could expand this one also as simply e to the x times e to the k. Then we will let e to the k to be k1. It's another constant. K is the original constant, but when that k is raised to the value e, it's another constant, so we could designate that one as simply k1. So the general solution for the given problem is y equal to k1 times e to the x. That's the general solution. Okay? Let's try to compute for the solution of the problem. Applying initial conditions, the initial conditions are x equal to 0 when y is equal to 2. It is this. Right? We are given this, so meaning the problem is asking for the particular solution, the exact solution. So going back to the derived general solution, y equal to k1 e to the x, substitute the value of x equal to 0 and y equal to 2. Okay? Y is 2, so this should be 2, equal to k1 times e raised to x, which is 0. But e to the 0 is equal to 1. Any number raised to a 0 power is equal to 1. So actually this is 1. So simplifying this one, 2 now will be equal to k1 times 1, or k1 is equal to 2. The unknown constant of integration k1 is actually with the value 2. So if we try to go back here, we put the computed value of k1, what will come out will be y. Y is equal to 2 e to the x. And this is the particular solution. Okay, particular solution, so that will be our answer. As simple as that one, guys. Okay, I will show you the importance of the derived particular solution. It is actually an exponential equation. It is an exponential equation. This is the y-axis, this is the x-axis. Okay, let's try to plot the graph. From the equation y equal to e to the, hold on, to e to the x. When x equal to 0, y is equal to 2. It is this. When x is 0, y is 2, 1, 2. It is this point here. When x is equal to 1, what will happen? Y will be equal to 2 times e to the first power. Or this should be 2 times 2.72 something. Or this should be 4, 14, here 1, 5.44. So when x is 1, the value of y is equal to 5.44. It could be this one maybe. Try to increase the value of y, or x rather. Okay, what will come out, since this is an exponential function, the value of y will increase. Okay, will increase exponentially. Okay, so if you try to plot the graph is something like this. Okay, as you increase the value of y, or x rather, y is going up exponentially. So if we try to connect the graphs, it is something like this. You don't notice it, guys? What kind of shape is that one? You don't notice it. It is a part of a missile. It's a part of a missile, maybe part from a submarine or a battleship. Okay? So that's the importance already of a differential equation. You don't notice it? Maybe the software they are using in the so-called design of the missile is differential equation. Because as you notice it, this part is actually a part of a missile. Right? It's a part of a missile that was fired from a battleship or a submarine maybe. Or a part of a missile that was fired from a land-based missile ejector. Okay? Oh, that's it. That's the importance of differential equation. So under DE05, under variable separable, we have related that the resulting particular solution was a part of a missile. That was fired maybe from a battleship or from a submarine or from a land-based ejector of the missile. Good afternoon, Los Angeles.